Okay, so we are discussing about the data path design that we may have with the memory instruction and the R type of instruction. So the R type of instruction like the ALU instruction. Okay, so we're discussing about the ALU instruction that the input the control unit will get the idea that from where I require to take the input. Okay, so that input will come from here. Okay, and here. Okay, and both are 5-bit input, and I think this is clear to all of you that from where this 5-bit will come, right? This is a part of instruction itself. Okay, so what will happen that in that case that the first input of the ALU will come from here, then second input of ALU will come from here. In that case the value of multiplexer input of the multiplexer would be 0. Okay, and also that the based on those 11, the first 11 bits of the add instruction or the ALU instruction, that it would be decided that which ALU operation is going to be performed. Okay, so that ALU appropriate ALU circuitry would be activated. Okay, and the output would be produced. That output will go like this. Okay, and it will be returned back to the destination register like this. Okay, from where the address of the register would come, so again it will come from the 5-bit of the instruction, the last 5-bit of the instruction, if you can recall that the instruction we had studied. Okay, so the data would be written to the this particular register. Okay, and this particular operation, this operation is known as the write back operation. Okay, similarly if I would be having the load instruction or the store instruction, in that case what is going to happen, let's see. So in the case of that load instruction, what will happen that the first 5-bit input would come from here. Okay, will go over here. Okay, so that value will go over here. Okay, like if you will see that the format of the load instruction is that like LDUR x1 comma x2 is the base address comma, let's say 10 is the offset. Okay, so from where 10 will go, so the 10, that 9-bit value will go over here. Okay, and it will go to the sign extension, so that will become 64-bit value, and this 64-bit value will go to the ALU as a part of input. Okay, so here we are going to have a base address, this is the base address, and this is what offset. Okay, so both would be added to each other. Now see, the output of the ALU is what, that is the effective memory address from where we want to read the data. So that address will go over here, right? This is the data this is the data memory. Okay, so in the data memory what will happen, that the address would always come from the ALU. Okay, and what will happen that right now we want to read the data, so that data would be read. Okay, and that would be outputted from here, so it will go over here, right, and through here it will go to the destination register like this. Okay, so I hope this is clear to all of you, that is the how the load will work. Okay, now suppose if the instruction is store, in that case what is going to happen, in the case of the store instruction the same thing is going to happen, that the first that the source input will go over here, that the immediate value will go over here. Okay, both would be added. Now this is the store instruction, means in that case what is going to happen. Please mute your mic. Please mute your mic. Okay, so what will happen that the first register, base register value will go over here, the app and offset will go over here, right? Now here in this case what will happen, that there is a source of register from where the value would go to directly to the memory. So where that value will come, so that value would come from here. Okay, and here you can see that the read port 2 would be used, so that that value would directly go to the memory. Okay, I hope this is clear to you. Like let's take the example of the store instruction, that store x1 comma x2 comma 0. Okay, so in that case what will happen, that whatever is there, value is there in the x1, okay, that's supposed to be stored into the memory. Okay, so this is how it is going to work. Okay, so if you have observed that in the case of store, we don't require write back operation. Okay, so this particular part is not going to be work. So okay, great. Now here you can see that we are having this blue highlighted values. Okay, all these are, so basically all these are the control signals that require to be generated by the control unit. Okay, so if I will tell you that if this the instruction which are currently we are executing is the store instruction, in that case that the what could be the value of mem2 register. Okay, so in that case that mem2 register is not going to be performed. Okay, so at that time this value would be x stands for don't care. Okay, because this is basically for what, write back operation, and there is no write back operation in the case of store instruction. But suppose if this would have been ALU instruction, in that case what could be the possible value of memory to register? The possible value would be 0. Okay, if it is the load instruction, then the input value would be what, 1. Okay, so this is how the control signal would be generated by the control unit. Okay, now in this case memory write, suppose if the it is the add instruction, in that case you don't care about that what would be the value of this, that either 0 or 1. Okay, right, so generally it remains don't care. Okay, so here we have understood about that the data path for the memory instruction and the R type of instruction. Okay, now this is a complete data path, right? Now here you can see everything that what will happen. So let me start with the fetch phase of the instruction execution. So in fetch phase, what will happen, that the instruction address would be fetched from the program counter register. Okay, once the address of instruction is available, right, it will go as an input to the instruction memory. It will go to the instruction memory. Okay, and that particular instruction would be fetched. Okay, the same time what will happen, that whatever the current value of program counter is, that would be inputted to the one additional adder that is available in our processor. That is, okay, in that case that the value of PC would be inputted to that adder alone, and the another input would have value 4. So the value of PC would be incremented by 4, and that would be updated into the PC register. Okay, now obviously I'm going to explain you that why do we have a multiplexer over here. Okay, now the second phase is the decoding phase. So in the case of decoding phase, that the control unit will get, hello, sorry, I don't know what was the issue. Okay, let me continue. So here the register, sorry, the control unit will get idea that which register I require to use for the reading, which register I require to use for the writing back the result. Okay, and this is the port where the data would come from the output. Okay, this is a port where data would be gone for the input. Okay, read 1 and read 2. Okay, and this particular thing is used for the immediate values. Like immediate values are either 9-bit or 19-bit. 19-bit immediate value is used for the arithmetic and logical instructions. Okay, and here we know that the shift left 2 is used for the jump kind of instruction. Okay, so here you can see that why do we have this particular multiplexer. Okay, let's try to understand this multiplexer, why do we have this. Okay, so as I have to discuss with you earlier, that the value of program counter can be updated by the branch instruction also. In that case, what is required, that we require to transfer the control of the program from one point to another point. Okay, but generally what happens, that the PC value gets incremented sequentially. Okay, now in the case of branch instruction, we require to jump the value of PC register to somewhere else. Okay, so that would be decided based on this. Okay, so here you can see that the value of PC would be added with the second argument of the branch. Okay, so both would be inputted into this particular adder. Okay, uh, and uh, and it will be outputted. Okay, now this particular multiplexer will decide, okay, based on the instruction. If it is the instruction other than the branch instruction, in that case that the input would be taken from here. Otherwise, if it is branch instruction, then input would be taken from here, and correspondingly that particular PC value would be updated. Okay, I hope this is clear to all of you. Similarly, we are having one more multiplexer over here. This multiplexer is used to find out that what will be the second input of ALU, whether it is the register or it is the immediate value. Like in the case of add I instruction, we take the second input from the ALU is the constant value. Okay, so that constant value would come over here, come from here. Okay, that is the extended value. Okay, but if the second value is the register, it will come from here. So either it can have value 0 or 1. Okay, similarly here we are having a signals of the memory rate. Where do you want to read the data in case of load, or do you want to write the data in the case of store instruction? Okay, and the last one is that what we want to do, we want to get the input from the memory output, this one, or we want to get the output of the ALU. Okay, and based on these control unit signals would be generated. Okay, so how ALU control signals would be generated? Okay, so here you can see in the case of load and store instruction, the function that we require to perform is the addition operation, right? The ALU operation that we require to perform, right? In the case of branch, we require to perform the subtract operation, as I have discussed earlier with you. And also we had discussed at the time of understanding the branch instruction that basically the subtract instruction has been used, and based on that the flags would be set, and based on the different values of the flags we can find out or we can compare the values which are provided hmm, which are provided as an input for that particular branch instruction. Okay, and for our type of instruction we are having a different we may have a different value of opcode. Okay, so here you can see for the ALU control, like for the AND operation, we have all 4 zeros. For OR operation, we are having 3 times 0 followed by 1 for add instruction. Okay, so these have the different value of bits that we can have for the different types of instructions. Okay, next here you can see uh, see what happens that when control unit will decode, at that time control unit just require to figure out that which type of instruction it is, right? Suppose if it is the load instruction and store instruction, control unit knows that which operation I require to perform, which ALU operation I require to perform, because in the load and store instruction, control unit requires to perform only addition operation, right? Similarly, for the branch instruction, it knows that I require to perform only that subtraction operation. Okay, so the code could be 0 1, and for R type instruction, that the controller will specify 1 0 ALU code. Okay, so we require only 2-bit ALU opcode. Okay, right? Later on, I'm going to explain that why I'm talking about right now only 2-bit of opcode. See, because the different types of instruction may require to perform the same operation. Okay, right? So that's why we can use the we can take the advantage of this particular characteristic. Okay, so here in this case for the load instruction, that it doesn't matter that whatever the opcode field it is, because it required to perform only addition operation. Similarly for the CPZ, but in the case of R type of instruction, it matters that what kind of operation that I require to perform through AL. Okay, I hope this is clear to all of you. Okay, so let's try to understand the instruction format, different instruction format that we have. Like that, if we are having R type of instruction, let's say the add instruction. So as I have told you that the first 11 bits are denoted as the opcode, that the next 5 bits are denoted as source 1, the next 6 bits are denoted as a shift amount. This particular field is used in the case of shift instruction only. Okay, this particular field is the source 2. Okay, and again it is a 5-bit field, and this is the destination register field, again it is a 5-bit field. Okay, like for the load and store instruction, that again 11 bits have been used as an opcode, but these bits are fixed value, like that if the value is 1986, then it is the load instruction, and if it is 1984, then it is the store instruction. Okay, the address is given over here. That address is the immediate value, okay, and this is a source 2 and this one is the destination. Is this clear that how many source bit value is there? It is a 9-bit value, okay, as I have told you that 9-bit value would be expanded to the 64-bit value, and the reason behind expanding this value is that our ALU takes 64-bit input. That is the only reason. Okay, for the conditional instruction, here you can see it is having a 6-bit of opcode field, okay, and here you can see that this is the 19-bit, okay, total 19-bit address, okay, that would be added to the program counter, and this is source register. Okay, I hope this is clear to all of you. Okay, so this is a complete data path, right? Okay, just we require to find out that what signals we require to perform a specific type of instruction. Okay, right? Now see uh, that we are having right now different control sorry, different like inputs. Like here we are having a register write, okay, then here we are having ALU source, okay, then ALU operation that we have memory write, memory register, memory read, and PC source. Okay, this is what we have seen. Okay, now the how control signal would be generated. Okay, so this how it is going to work. Now I think this would be clear to all of you. So here, after completion of the fetch phase, what will happen that the instruction is of size of 32-bit, okay, 0 to 31, okay, so altogether 32-bit. So what will happen that the bit number 5 to 9 will go always as an input, then bit number 16 to 20, another 5 bits will go as a second input, then bit number 0 to 4 may also go as a second input, okay, right. Then then here you can see that the whole instruction 0 to 31, and among that it depends that which bit would be extracted. So here if it is the then load or store instruction, only 9-bit would be extracted for the sign extension, or if it is the branch instruction, then 19-bit would be extracted and the sign extension operation would be performed, so that the 60 it would be converted into 64-bit and it will go to the ALU. Okay, I think this is clear to all of you. Okay, so here by seeing the first opcode bit, that control unit get idea that what I supposed to do, okay, whether it is a branch instruction, whether it is ALU instruction, okay, like that it required to perform memory to read the operation, okay, in the case of that load instruction, and memory to register operation, then ALU operation, memory write operation, ALU source which I require to perform, and register write. Okay, see all these operations are common across all the instruction, and that's why they have written over here. Okay, so if you see this particular data path design carefully, there are two different control units. Okay, this one is general to all the instruction and this one is specific to ALU. Like here you can see that ALU operation would go over here, right? Okay, it will just give the idea, it is just 2-bit values, 00, then 01 and 10. Okay, 00 means it is the load or store instruction, 01 means it is the branch instruction, and 10 means ALU type of instruction. Right, okay, and if it is ALU type of instruction, then again that the bit number 31 to 21 will be inputted over here, so that it will get the idea whether it is add operation, subtract operation, multiplication operation, division operation, or any other operation. Okay, so based on that, that would be that is defined that which kind of operation it is. If it is 00 and 01, in that case this ALU control will just ignore that. Okay, right, so this is how it works. Okay, like this is a instruction sorry, data path diagram for the R type of instruction. So in that case what will happen, this particular grayed area is not going to work because this belongs to the that branch instruction. Obviously this is also not going to work because this is memory operation, this is also not required because this is the expansion of the constant value. Okay, so only the thing that is required is which is the highlighted bold. Okay, so please try to interpret like that. Suppose it is the load instruction. In that case, again, this particular part is not required. Okay, now this part is required because this is the memory unit. Okay, right. This one is not required. Second input of the register is not required. Okay, so this is not going to use, but the extended value is going to be inputted into the ALU. It is like that. Okay, for the branch instruction, okay, that this one is not required. Obviously we require ALU in this case, but we don't require that 31 to 20. Obviously this value will go over here, right, but it is not going to be used. Okay, right, so we don't require write register, we don't require write data, etc, etc. Okay. So suppose here we have discussed about the conditional branch, but suppose if we require under unconditional branch, right, that we haven't discussed the specific like format of the unconditional branch is like this, that it has like 2 bit sorry 4 bit value, like not 4 bit, 5 bit or 6 bit, 6 bit value. Okay, that which type of instruction it is. Okay, and along with that we are having 26-bit address value. Okay, right. So what will happen in that case, that the PC value just would be added by this 26-bit value. Okay, so what happens that the top 4 bits of the old PC value would be taken. Okay, then the remaining 26, not 26-bit, 28 bits would be filled with the 26-bit which are available over here, and the last 2 bits would be added with the 0. Okay, so can you tell me the reason why we are having last 2-bit value that is updated to 0, sorry, would be 00, appended with the value 00? Because we require to shift that whatever value is there as an address. Okay, we have to align with the block address that we have in the memory, and as we know that the memory is always at the offset of 4, and that's why we require to shift left shift 2 times. So that's why that's 26 bit value followed by 20, so that is the 2 time left shifted value. Okay, right, so this is how the unconditional branch will work, and here you can see this is how it is going to work. Okay, so that will go over here. Okay, that the 26-bit value will go over here. Okay, that will become the 64-bit value. Okay, and that will be shifted by 2. Okay, and finally that the value would be updated to the program counter. So obviously here that what are the performance issues? The performance issue is that the longest delay determines the clock period. So I don't know whether you have observed or not, but see, whatever operation, these 5 operations that we have understood, okay, all those operations require to be performed within a single clock cycle. If you don't perform all the operation in a single clock cycles, then you are not going to have a proper result. Okay, right, so keep this thing in mind, that whatever design that we have seen right now is a single clock cycle design, and which is not efficient design. Okay, so this is not feasible to vary period for the different instruction, because some instruction takes a shorter period and some instruction take the larger period. Okay, so that is what we are not going to manage using this, because what we are going to do, we are going to keep the cycle time fixed constant for any type of instruction, and that violates our design principle, that is the making the common case fast. Because like if you might have observed that the jump instruction takes very less time for the instruction execution, it is just matter of like updating the value of program counter, and that is what we require to do. Okay, so we can get the idea that the jump instruction takes very less time to perform the instruction execution, and that's why we require to discuss about the multi-cycle instruction or data path design. Okay, so we can improve the performance. Okay, and basically the pipelining that we have understood earlier in the earlier lectures, right, it uses the multi-cycle design. Okay, so in next lecture I will give you idea about the how we can incorporate the multi-cycle design with the data path that we have just designed. Okay, so that's it for today. Right now, if you have any question, then you can ask me.
Sir,
Yeah.
uh, in the whole data path design, the data too is directly fetched into the memory. Why?
Sorry,
Can you take to the R type instruction whole?
sorry.
Uh, yes, sir. In this, the this data to is why is directly taken into the memory.
Uh, Data to this one, na?
Yes.
Okay. So like consider the load instruction. Load instruction has a format like load x1 comma x2 comma 0. Okay, right? So what is x1? In that case,
Yes.
x1 would be the source register
Yes, sir.
that we require to store into the memory. Okay, so in that case what will happen, that
Yes,
the
sir.
whatever value of x1 is there, that would go to the memory, whereas the second register that we are mentioning, that will go into the ALU along with the offset that we have over here, right? Okay, so both would be
Yes,
added
sir.
with each other and we will able to find out the effective memory address.
Yes, sir.
I hope this is clear to you, because this second register input will directly go to the memory, the data that we want to write to the memory.
Yes, sir.
Is this clear?
Yes, sir. Thank you, sir.
Okay, okay. Any other question? Any other question?
Sir, what is REG2 lock?
REG2
Lock
lock.
first in the
This one,
control.
this one. See, from where, which register we are considering. Okay, so see here in the case of that the compare instruction. Okay, the input may come from this particular field value. If you might have observed that the instruction format that I have shown for the compare instruction. Okay, so that the source register can come from the 0 to 4. Otherwise what happens, that the 0 to 4 bit always dedicated are the destination register. The only exception is which one? That the compare instruction. In the case of compare instruction, this 0 to 4 is used as a source register, and that's why we are having this REG2 lock.
Yes.
Okay.
Yes, sir.
Hmm. Any other question?
No,
I
sir.
I hope you have understood all these things right now. That would be easy for all of you to understand. Okay, and those who could not join the lecture, please try to share that whatever you have gained from today's lecture. Okay, and still if you are having any question, you can post those questions or you can call me. I will try to solve your doubt. Okay.
Thank you, sir.
Yeah. Okay. Thank you all of you.